So the biggest lie on Earth, believe it or not, objects don't accelerate down in free fall. It's the other way around. It's the Earth that's coming into contact with it. So the Earth is pressing up against us right now, and that's why you have weight.
Well, then you would not be able to have a sphere because it would be going in all directions.
Exactly.
Okay.
You get it. You get it. You gave me chills right now because you're understanding, man. But yeah,
funny.
no. But yeah, the Earth.
But I feel like one has to answer two questions.
Right.
One, why is it that this person who's on YouTube, for instance, not you, no offense to you, but has figured this out and all these other folks haven't? Not impossible.
Right.
But also, how has it been kept quiet? Because even like, if we imagine an Earth being a flat disk, which you have not said it is, I'm saying, as a sea captain, for a couple hundred years, sea captains, how would they not have known how far they traversed? How would we maintain such a
big lie, right, from the people, right?
Yes. Yeah. How would that happen?
Hey, what's up, man?
How you doing?
Doing good. You want to give this a shot?
Okay.
Yeah. So I have 3 very easy questions, and I want to see if you could get 2 or 3.
I don't think I can get any, but okay.
No, I know you will. You will. It's very easy. So when we have air, they actually have to do with the orientation of water.
Okay.
So when we have air and water in a bottle like this, and the bottle's at rest, the water will always go down and push the air to the top. Again, regardless of the orientation of the bottle, water will always go down and push the air to the top. You know, that's a fact. So since we understand that fact about how water behaves when it's at rest, right? I'm showing you these 2. Which one of these 2 water bottles is not in the correct orientation? 1 or 2?
2.
You got it. Yeah. So why would you say number 2?
Well, the water is
on top, right?
Yeah.
That defies physics, right? So
yeah.
I actually took it like this.
Yeah.
Yeah, you're right. You got it. So that's you already got one.
There was maybe a trick with the coloring, so that's why I was taking my time.
I usually no. That's a good thing. The water is blue. I painted it with food coloring.
So it's more apparent.
Yeah, so it's more apparent exactly.
Okay.
So no, yeah, you got it. Even without the water, you know. Now, another thing about water, again, regardless of the orientation, water always finds its level. You know, that's a you know physics of water. So another word, what could be another word for level? We have to use a different word. When something's leveled out, that's a good one. Horizontal will be the one word definition. You know, because you could have a straight line that's on a slope. It's not level. You know, it has to be a horizontal straight line. That's what level. So since we understand, again, water always finds its level, especially when it's at rest. So which one of these 2 represents level as we know it when it comes to the water?
On our scale?
Yeah.
This one.
Yeah, like if we went to a giant lake that was at rest, right? The body of water was at rest.
Okay.
Yeah. A, right? That's the obvious one, right?
If it's not too giant, yes.
Okay. All right, so now, so you got this one, right? Water level. So this last one is like the hardest one, but we'll see how you do. So I have 2 images here, and the reason I call them images is because one of them's a photograph and one of them's a painting.
Okay.
Well, actually it's CGI, so it's a computer generated image, and one of them's a photograph. So I want to see if you could tell which one is the photograph.
Oh, this is the photograph.
You think it's a photograph?
Yeah.
It was actually a trick question. They're both CGI. Yeah.
Too big?
Well, right? Well, here's the thing. There is 3 reasons. I don't expect people to get this one, obviously, because it's a trick question. But
I should have taken my time.
Right? So there is 3 reasons why I asked this question, though. The first reason is just believing someone opens the door to being deceived, right? So it's not good to just believe someone, right? So the second reason is if we want to determine something is real, an image is not good enough. Because I could show you an image of me flying, but would you believe I could fly?
Sure.
All right. Especially if the image defies physics, right?
Yeah.
So the third reason why I'm doing this is because these images actually defy physics. You want to know how these defy physics?
I do want to know.
Okay.
Can I have 1 second to think about it before you tell me?
Sure.
Okay, go ahead.
Okay, so the reason why these images defy physics is because NASA, these are official NASA images, by the way. This one's from 2002 and this one's from 2012. But again, they call them images because they're not photographs. They make them in a computer. And the reason why, again, is because these photographs from the Earth don't exist. And the main reason is because the Earth is not a ball. So NASA claims to have satellites orbiting the Earth, right? So they need to know the radius of orbit. So they need to know the radius of the Earth that they're supposedly going around it. So they do tell us the radius is 3,159 miles, which gives us a circumference of 24,901, which means there has to be curvature every mile. And every mile has to increase because they're saying it's a curve, not a slope. So in the first mile, there's an 8-inch drop. Second mile, 32 inches, and by the third mile, there should be 6 feet of curvature. So again, if we go to physics,
from north to
from the starting point, straight out, basically, if we're measuring straight out from, because we're supposedly always on top of the ball, right?
Okay.
That's what they claim, right? So if we were to measure, straight out, then the water, especially, a lake, if we went to measure a lake, that water should be bending at the rate they're telling us. So again, if we went to a giant lake to physically measure for this curvature, the water is going to show us, the physics of water, it's going to show us that it's going to be level.
If it's small enough, yes.
So you believe that in a larger, so a lake that was 5 miles across, for example, you believe that the surface of that lake is bending?
I don't know what the minimum distance one would have to be able to measure
a 1 mile,
but large enough, yes, it would necessarily curve.
So you think in 3 miles there's 6 feet of curvature?
I don't know what the numbers are.
Well, that's why I'm here, to show the numbers. These are the official NASA
Yes, but
numbers.
You've already proven to me I shouldn't believe you.
Oh, exactly. Don't believe me. Understand how water behaves.
Yeah,
that's the thing. They could claim that the Earth is twice this size, right? Half of this curvature should still be there. You could claim it's 4 times the size. Curvature should still be there. Fact is, the physics of water doesn't have a form. It only takes the shape of the container, and the surface always collapses. It always forms an equal surface. It always levels out. That's the physics of water: measurable, testable, repeatable. There's a reason. Have you heard of the term sea level?
Yes.
How they describe the oceans?
Yeah.
Right. That's how we measure height and depth to be congruent with each other. That wouldn't work if we're measuring from a curve. Everything, all the blueprints, for example, in engineering that people use to construct railroads, bridges, they're all basically don't take account of Earth's curvature. All the blueprints are basically done from a datum line. Yeah. Basically. But that wouldn't be the case if the Earth was a globe. Those calculations will have to be taken into effect, especially when building bridges that are miles across, but they don't. So all the blueprints show that there's no curvature as well. All the plans, engineering, construction.
Well, I think that one assumption you have is that they're measuring, if they're building a bridge, they're measuring up from sea level.
Yeah, my point is that the blueprints, the plans, that they don't take account of Earth's curvature. They actually assume is a level plane. They actually use Euclidean plane geometry.
Yeah.
They don't use non-Euclidean.
Yeah. Because we don't make bridges that are traversing this huge distance where you would have to.
In China, there's a 100-mile long bridge.
Yeah.
So there are bridges that are miles across.
Sure.
And if we're talking miles, then we're talking feet in curvature. The more, every mile increases more and more and more because again, it's curving, right?
So let me say, I just moved here from. It's kind of hard because there's a cloud occluding it.
Right.
But Oregon, down to Southern California or something here is 1,000 miles.
Sure.
It was 980 or something on my speedometer.
Sure.
Okay.
Sure.
So 100 miles is a teeny little thing.
Well, let's look at how much based on the radius they give us. 100 miles. Here we go. Miles.
You said the bridge was 100 miles.
Yeah, there's 100 miles. So 100 miles. They should be in feet. There should be 6,669 feet.
How does that work?
That's the curvature formula based on the radius of the Earth.
So, just so I follow you, because the part when you talked about the curvature initially, I didn't quite follow you because it was too fast.
Okay.
So you're saying you're here, and if you go out 100 miles, then you're saying the drop down here is
6,669 miles. Yeah.
Well, I would say that doesn't make sense to me.
Why doesn't it make sense?
In feet. Sorry.
Yeah,
so you're
feet.
a little over a mile you're dropping.
Yeah,
so 100 miles, a little over.
Yeah, the miles.
I see.
Yeah. Obviously, when you put into miles, it's not so much, but when you put into feet, again, this is probably taller than. It's probably taller than this. 6,000 feet for sure.
Oh, yes.
Yeah. This is
by quite a distance.
This is this is not even 500 feet probably.
No.
Yeah. So think about that. There should be that much curvature, over the water, but it's not there. You know what I'm saying? And again, there's lakes that are 20 miles across. Big lakes, giant lakes, the Great Lakes, right? In 20 miles, 266 feet in 20 miles. That's how much water should be bending, on a lake. But we understand, at least me, I understand the physics of water. Again, it doesn't matter the size of the container. Water always has to be contained, and the surface is always going to form a level surface.
Well,
that's the physics of water.
How shall I say this? You've taken calculus.
Oh, sure. Yeah, I understand math. What do you understand? Sure.
So you understand that we use each point as a flat on a curvature.
Okay.
When you're calculating.
When you're building locally, I get that. Yeah.
Yeah.
But when you're building at a distance,
so then for the size of the Earth,
right,
this is essentially a point.
Yeah.
Right?
I
so it's going to appear flat to us.
Okay.
Right?
Sure. So let's say, so you're saying that the whole lake is one big point? Like
No.
So there should be deviations on that lake then, right?
There should be a curvature if the lake is large. I don't know the number, and I understand you have the. I'm just saying, me personally, I haven't ran the calculations. The Pacific Ocean should have a curvature.
Okay. So so that lake shouldn't?
If it was large enough, I don't know how big it has to be before you measure. You know.
So let me ask you this then.
So you could say that. It's not,
right.
But to be an extreme, to illustrate a point, to be artistic, because this would maybe have a slight curvature, right? But it would be so infinitesimally small that we couldn't maybe measure it or something. You see what I'm saying?
At the distance of what, the lake, you're saying? So let's say it was a 10-mile lake across. You're saying that there might be a very small curve there, but we just can't measure it?
Well, I mean, if we say that the Pacific Ocean is curved, well, then we'd have to say a smaller thing is also curved, right?
Exactly. Yes. Yeah. Okay. Yeah. So maybe
I just didn't understand what you're saying.
Okay. So you basically believe that the curvature is.
I don't believe anything.
Okay.
But
so let me ask you this.
I would say the thing that has made most sense to me is that a large enough scale, you see the curvature, where a small scale you do not.
Okay. So if I was to ask you, what's the number one thing that convinces you that the Earth is a ball?
Oh, I used to live right here on the Pacific coast.
Okay.
Right, I mean literally
sure.
on the ocean, and you can see the curvature.
The horizon. What
yeah,
you're saying. Okay.
The ocean. You look out over the ocean; it's curved. Yeah.
So I actually have images of the horizon here, and this is 20 miles in height. How would you describe the horizon here?
Okay, it's 20 miles in height.
Yeah.
And how wide is it here?
I actually don't know.
Because it doesn't matter the height. It matters.
This is probably like 1,000 miles, probably. Who knows? Probably 1,000 miles, roughly. It's more than 100, that's for sure. My point is, how would you describe that horizon geometrically, if I were to ask you that?
Well, the obvious answer is flat.
Horizontal.
Or straight.
I would say the word horizon comes from the word horizontal, right?
Okay.
So the only place you're ever going to see curvature of the Earth, and it's going to be through GoPro cameras like this. I don't know if you're familiar with the fisheye wide-angle lens. It curves horizontal lines.
Yeah.
So you're only ever going to see curvature of the Earth through fisheye lens like this, or through CGI images like this.
Well, you have a very small area here with an extreme curvature, right? Obviously, we both agree that is not
exactly. But they're using the same effect when they're very high, though.
Yeah, but I'm saying no effect. My eyes.
Have you seen the Red Bull jump, for example? You never seen the Red Bull jump when they did a jump from the edge of space, supposedly?
Oh, I know what you're talking about, but I don't think I watched the film.
Okay, I have a 20-second...
but I'm telling you, friend, that I've stood almost every day. My wife and I go walk, through our yard to the edge, and we'd look out, watch the sunset and stuff, and you can see a curvature.
So you're saying that you're seeing a curvature from sea level from left to right?
Yes.
But why isn't that curvature here when we're even higher? That curvature should be more prominent the higher you go.
I don't know, because I don't know how light works with the higher levels of the atmosphere.
Okay.
No, I'm not trying to be cheap about it. I'm being real.
I understand refraction. You're talking about refraction, right?
Yeah, I don't know enough physics to be sure of my answer.
Here's another thing about the horizon that a lot of people don't know. The horizon is not a physical thing because it changes due to your height, right?
Yeah.
So
your eyes, you can't see.
For example, if I was to hold this water bottle and then just move away from you, a mile, eventually you won't be able to see it anymore, right? Because it just reduces in size due to perspective, right?
Yes.
The horizon is basically our limit of perspective.
Yeah.
So it's just how far we can actually see. If you elevate, you basically increase your angle of view, and you're able to see further in front of you. So when you elevate, the horizon should never rise with you or appear to rise, but it does. If it's a curve,
well, unless you're going around.
No, but if you're just going straight up, but if you're just going straight up,
the horizon be dipping,
But that never happens in reality. The horizon always rises with you. It's always in front of you, the horizon. And if it was actually curving down, when you elevate, you should look down at the horizon, but you never do.
I don't quite know what you mean when you say that it doesn't go up. I mean, if you're on the...
it doesn't appear to... let's say you're on top of a hill, right? On a very slight slope hill, right?
Okay.
If you're on top of a hill, when you elevate, do you think the bottom of the hill is ever going to rise in front of you?
No.
Exactly, right? So if the Earth is supposedly curving away from us, like at an ocean, when we elevate, the end of the ocean, basically, or the further we look, it should never rise in front of us if it's sloping down like a hill.
Do you mean rise, and that you would be able to see more and more of it?
No, but it rises in front of you. So you're just looking straight out at the horizon. When you elevate up, the horizon should never appear to rise with you. You should look down like this. But that never happens.
It goes like this, and you can see more.
Yeah, that never happens, basically. That doesn't exist. So the Earth is just an extended plane. And again, the horizon is just how far we can see. When we elevate, we're able to see more of it. But it's just across. It's not going down like a hill. You know what I'm saying?
So how would GPS work then?
Well, GPS is just using ground towers and cell phone towers, basically.
Okay, well, I'll say satellites then.
Yeah, so I don't know if you knew, over 97% of the communication here on Earth is done through underground and undersea cables, fiber optics.
Okay.
So that's over 90. That's the internet right there, basically. It's underwater cables. So all these satellites or signals that are coming from above, there's I don't know if you knew, Google had a project called Satelloons. Oh, so they're basically satellites but on balloons, like helium balloons.
Okay.
You know, so NASA is actually the #1 buyer of helium, and any signals that are coming from above are literally just coming from Satelloons or high altitude drones, basically, which is basically for the military.
So I assume that you're positing then that there aren't satellite photographs from space, just from balloons.
Exactly, it's just from balloons, and again, you can't go high enough to take a picture of the entirety of the Earth.
So I assume you're saying, or you would agree, that then the famous photo in, I don't remember when in the 60s they took it, the first picture of Earth.
Yeah, the 1972 picture.
Okay.
So that one, not only
because it was after. It was after 16.
Yeah. So that actually, not only that does that image defy physics, the physics of water, but there's different ways people have debunked it. So I mean, this is not a really good way to debunk it, but people have are you familiar with the date and time website? Like you put a date, time, and it shows you the position of the sun on the Earth.
No, I didn't. But okay.
Point being is that they took that image of 1972, the exact date and time where they supposedly took the picture.
Okay.
And then basically the sun, how they took it just doesn't fit. Basically, how the sun should have been positioned on that date, on that time.
Okay.
So it basically contradicts that whole. So that's only one, but again, the physics of water is going to show us that.
Let me ask you a question, because I think I might know where you're going.
Okay.
So this is my issue. So there's been generations of scientists, yes?
Yes.
Geographers, cartographers, atmospheric scientists, on and on and on, right?
Sure.
I mean, that have devoted their life to studying this phenomenon.
Yeah.
That does not mean it's correct, their conclusions, or to what degree it's correct.
Exactly.
That does not mean that someone outside of academia or research could not find a better model or a more something that illustrates reality better.
Yeah.
I agree with all those premises. But I feel like one has to answer two questions. Right. One, why is it that this person who's on YouTube, for instance, not you, no offense to you, but has figured this out and all these other folks haven't? Not impossible. Right. But also, how has that been if it is a conspiracy, how has it been kept quiet? Because even if we imagine an Earth being a flat disk, which you have not said it is, I'm saying, if we imagine it so, as a sea captain, for a couple hundred years, sea captains, how would they not have known how far they traversed since the chronometer in the 1700s? So it gets to be a point where I'm like, well, how would we maintain such a
big lie, right, from people, right?
Yes. Yeah. How would that happen?
So very easy. First of all, first navigation, right? You're talking about navigation. How is it that navigators haven't figured this out, right? I don't know if you knew, navigation, especially when people navigate over sea, they use the celestial sphere, right, concept, right, when they measure angles of luminaries dipping in the horizon. So I don't know if you're familiar with nautical miles, that's used for navigation, right?
Yeah, and it's too rusty for me now.
So I'm just going to do a quick overview of how that works. So a nautical mile is measuring the degree of angle change from the distance you travel from like a lighthouse, for example. So when we're traveling over water, when you notice a 1 degree change of height drop, right? For example, they're claiming that we're going over a curve, and that 1 degree change happens because you're going over a curve, right? The reality is, again, because we have a limit to perspective, and everything shrinks to a point. Everything shrinks to a point. That apparent drop has happening due to our eyes, basically. So the celestial sphere that we use to navigate is based on the eyeball. Okay. So because our eyeball is a sphere, obviously a ball, and because of perspective, everything shrinks to a point. The apparent drop of luminaries is based on perspective and not the curve of the Earth. A lot of navigators, they don't know that. They just believe, that Earth is a globe, so we're going over a curve, They don't really think about the...
Let me say it this way. Maybe it'll make it clear. So if one imagined this particular model, which you have not posited, so I'm not saying you're saying this, if we imagine the North Pole in the center of a disk, Antarctica around the outside, to traverse time-wise, not even taking measurements, other than your sense of passing time, if you traverse from the southern tip of South America to South Africa, you would be taking one of the longest transits. Yes?
Yeah.
So you would know that this is taking weeks, months, whatever it is, compared to just going a little ways. Would you? I mean, that kind of seems like common sense to me.
I agree. I would say.
So then, how would all these whalers for a couple hundred years? They never realized how far how long it took them, or merchant ships.
Right. So real quick. Again, I don't claim this is what the Earth looks like. The fact is, nobody knows the true layout of the Earth. So I would say this map is also a psyop. Because this was derived from vision, and this is just the opened up version of this, right? Literally, it's the same continent, it's the same basic layout, basically. But just
mapping it.
I don't agree with any of these, but I'm just gonna, because you're talking about how can we fly from here to here, right? Because it will be far opposed to on a globally short, right? That's your point. I don't know if you knew, when you take a flight from Australia to, for example, Africa or South America, I don't know if you knew, a direct flight doesn't exist. The flights always stop. Like, for example, if they go here, they always stop in North America, and the excuse is that they do that to get fuel, and then in other words, they just do a straight line on this map. On a globe, it looks like they're going up, and then they're going back down. But in reality, they're just going in a straight line across. But they have to stop here to get fuel, because obviously it's long distance. But on a globe, they just go up and then come back down.
I haven't seen it that
direct flight doesn't exist.
I've seen it the opposite way, where someone took a line on a sphere that whatever goes like this, and then you project it onto a two-dimensional surface, and then it seems arbitrary. It's odd.
Actually the other way around. I see. I know what you're saying. It looks arbitrary on this, and in this is just straight lines.
So so what is you feel a more accurate model?
So I'm going to tell you the fact. So you've heard of flat Earth, obviously, right? So the Earth is not flat or a globe, and I'm going to tell you why. So people that are claiming the Earth is flat, they're also claiming that it's motionless, so it's just static, right? That doesn't
try and account for the celestial bodies.
I don't know why, but that's just retarded. But the fact is that the Earth has constant motion. So I don't know if you knew gravity. They claim that a force pulls this and accelerates this towards the ground. I don't know if you knew that. That's been debunked. Have you heard of Einstein's theory of relativity?
Yes.
Yeah, right? So he acknowledged the fact that this doesn't accelerate towards the ground, or it doesn't get pulled or pushed down towards the ground, because one of the simple, I don't know if you knew how an accelerometer works. So if you have a tube with water and it has an air bubble, when you accelerate that container, basically, the bubble displaces relative to the direction of acceleration. So if you accelerate, the bubble gets pushed towards the front.
Yes, because it's less dense.
Exactly. So it's all relative to motion, right? So when you accelerate this towards the ground, there's no effects of motion. So if you have an air bubble on a container and you let it go in free fall, that air bubble, not only does it should go down, but it doesn't. It just stays frozen. So basically the air bubble is showing you that this is not being accelerated down, and it's just decelerating. And the reason why is because, again, the Earth is in constant motion. So when you release this, it's no longer connected to the Earth, because it's connected right now through me and I'm connected to the Earth. But as soon as I release it, it's no longer connected to the Earth, so it loses momentum. So the biggest lie on Earth, believe it or not, objects don't accelerate down in free fall. It's the other way around. It's the Earth that's coming into contact with it. So the Earth is pressing up against us right now, and that's why you have weight.
Well, then you would not be able to have a sphere. because it would be going in all directions.
Exactly.
Okay.
You get it. You get it. You gave me chills right now because you're understanding, man. But yeah,
funny.
no. But yeah, the Earth will have to be expanding if that was the
Okay.
case. So that's the biggest lie on Earth right now because again, even Einstein had to address that, and he came up with the bending and warping of space-time, which basically just talks about inertial reference frames, explaining that it's the mass warping space, and that's what gives the illusion of falling.
But if everything's expanding, or you're positing only the Earth.
Only the Earth is moving upwards uniformly.
So you're not saying the whole universe is expanding?
No. What's outside of the Earth is a contained system. So if you ask me what's outside of the container, I don't know. That's where outer space and all that it's just religion. Nobody knows.
Okay.
You know, negative pressure systems next to positive pressure systems without a solid barrier don't exist. So people claiming that outer space is basically a negative pressure next to Earth's pressure without a solid barrier. Again, their explanation is that gravity, this force. Again, the number one lie that objects get pulled down. That's how they explain away the whole model.
So again, you would not be able to have a sphere.
You won't be able to
you
have
wouldn't
a
have the
sphere.
atmosphere.
Exactly.
So what is the shape that you imagine?
It's a level plane that's in constant motion. And it's, in my opinion, it's being contained by some physical barrier that's basically keeping the air in here. That gives us our pressure.
I'm sorry, it's a little bit slower.
Yeah, so we have air pressure here, right? The reason why we have air pressure is because the air is being contained. That's what physics shows, you know? So the Earth shows us that it's in constant motion and being contained. But what's outside of the Earth, outside of this reality that we experience, I don't know. That's unknown. So that's, if you ask me, is there a way to find out I don't think so, you know? So why are they lying? It could be just because... It could be many reasons, to be honest. I don't even know why they're lying, to be honest. All I know is that they are lying. You know, this place... Oh, here's the thing. This place was created. That's another thing. The first law of thermodynamics, energy cannot be created nor destroyed. It can only transform from one form to another. That proves that this place came from something else. So this creation didn't come from nothing. You know?
Is someone saying it's coming from nothing?
Big Bang. Big Bang, evolution, you know, that basically came from nothing. You know? So anybody trying to tell you how this place came to be, how it was created, is just a religion.
I'm now disagree with you in spirit of that claim, but I'm going to say that as far as I know, though, astrophysicists and stuff don't claim to know.
They say it's a theory.
Well, no, you know, in the very beginning, I don't remember the length of time.
Okay.
But it's not that we can look in our telescope and see the Big Bang.
Okay.
Because there's no light.
Exactly.
Right?
Yeah.
So I think that there is a great level of not knowing what happened is when you go far enough back and approach the Big Bang.
Right.
So, but I also, you know, we can have what's the lower limit on the density of mass?
Right.
You know what I mean? We could have a very small structure that it would be have incredible mass. Okay. I'm not an astrophysicist.
Right.
Maybe there's a reason you can't.
Right.
But so that you could still have something. It's not actually from nothing. I mean, what is that called? Like ex nihilo or something that's from the Bible is created from nothing.
Are you talking about kind of like CERN? You're familiar with CERN? They're kind of supposedly splitting atoms, or trying to split atoms. Because again, like you said, supposedly splitting an atom is what caused this explosion, you know. That's a very dense.
Big Bang?
Yeah, the Big Bang. It came from a very dense point where you're saying.
Okay, I've never read anything that they knew whether it was.
Well, that's what they theorize.
Came from.
Because obviously they have to warp the model to fit physics. Because again, like you said, nothing can come from nothing. So now they claim it is like an infinitely dense point. So everything exploded from an infinitely dense point. Which, in my opinion, that's just you know.
I guess I'm a little simple-minded. So to me, if you can't demonstrate something. If you can't test it, I think it's a little outside the bounds of science.
Exactly.
And I'm not if you've seen my shirt, I'm obviously, you know. Well, why? Okay. Well, yeah, you're a pope now. Why? Because who says the Catholic Church gets to be the only one that make popes? I mean, it's all made up, right? It is. I'm not. I think that physics, in the extremes of cosmological or atomic particles, there gets to be a limit of what we know how to test at this point, and then beyond that, you can agree or you can believe whatever interpretation of quantum physics you want, but unless you can demonstrate it, that's just a belief.
Right. So again, That's true. So when it comes to physics, though, we could prove things to ourselves using physics. That's how we're able to build cars. You know, we could prove that, you know, expansion of gas can push a piston, and you know, we can make a car move based on that. So if we could prove that, you know, certain things in this reality, you know, with physics, for example, then surely, you know, if claims contradict those proofs, then we got to throw those claims out, especially if those claims don't have anything practical, right?
Or work on that model to build in.
Exactly. So again, the fact that objects, you know, don't accelerate in free fall, again, to me, is like the biggest.
Yeah. Do you have any like a video of the bubble?
Actually, dude, can I show you that?
Yeah.
It's a 2-minute video. I actually did it myself.
Not that I believe videos.
No. You can recreate this yourself. That's the thing. So here, I'll show you this video. I just uploaded it like a week ago. And it's called Buoyancy Proves the Earth is Not a Motionless Plane. So it's a 2-minute, 30-minute video.
Okay.
Check it out.
Oh.
It's like the air bubble.
Let me rewind it.
Okay. So this is the setup for the first of 2 buoyancy experiments I'll be doing. A water bottle as the container, and the camera mounted onto the reference frames that I'll be accelerating, which is the dolly. The reason why we have to constantly accelerate to recreate buoyancy is because we're connected to the Earth, which is already in constant motion. And in order to overcome constant motion, you need constant acceleration. As you can see, the air bubble is centered, which means the bottle is level and at rest. The air bubble will always be displaced or pushed relative to the motion of the bottle. When I accelerate the bottle, the pressure of the bottle pressing on the water creates a pressure gradient. The water is then able to push anything that's less dense, like the air bubble, in the direction of acceleration, which is what we will call buoyancy. You can't have buoyancy without a pressure gradient, and you can't have a pressure gradient without a contained system that's in motion. For the second buoyancy experiment, I have a cargo van as the container, a helium balloon, and an apple. I also have the camera mounted onto the reference frame that I'll be accelerating. As soon as I accelerate, the pressure of the van pressing on the air creates a pressure gradient, with the most dense air towards the back of acceleration and the less dense air towards the front. The air is then able to push the helium in the direction of acceleration because it's less dense. But the air cannot push the apple because it's more dense, therefore the apple remains at rest. The apple only appears to move in the opposite direction of acceleration because the camera is also moving with the reference frame. The helium balloon has true motion and the apple has apparent motion. In order for the Earth to be motionless, you need a force moving in opposite directions at the same time to be able to accelerate the apple in one direction and push the air and helium in the opposite direction without any motion of the container.
Sorry.
Also need this same force to accelerate a container without any displacement or buoyancy. In other words, you have to believe in a magical force that can accelerate a container without any pressure or buoyancy, and also be able to create pressure and buoyancy in a motionless container, which is the literal opposite of what physics shows. Physics proves that you can't have pressure and buoyancy without motion of a container, and you can't have motion of a container without pressure and buoyancy, proving that the Earth cannot be a motionless plane.
So again, when you release a helium balloon and you release an apple, only the helium balloon has true motion because it's being pushed up. I don't know if you knew buoyancy is considered an upwards push. It's a force. The apple, on the other hand, again, that's why Einstein had to address this. The apple only appears to go down because we're all in motion. Everything that's connected to the Earth is actually moving. You know? Okay. So when you release an object, it only appears to go down, but it's the Earth, everything that's coming up.
I understand what you're saying.
Yeah.
So if I give you all of that, then, or is that what you're trying to say? That, hey, this doesn't add up, that you're not making a further claim, that is your claim.
Yeah.
That we couldn't be a sphere, because we would have to be moving
the Earth,
with...
Exactly. The Earth has to push up on the air for the air to push up on helium. Or even if you have a pool, the Earth needs to be pushing up on the water so that the water can push bubbles up, which is what air bubbles, that's why air bubbles rise. So there's a force going up, measurable, basically.
I follow you. So, so imagine we're in a plane, like you're positing, moving like this,
straight forward. Yeah.
So then you would have a pressure gradient
That's the thing. You have to consciously accelerate to recreate the pressure gradient, because I know what you're saying. In the airplane, you're technically not connected to the Earth directly, right? But I don't know if you knew, the reason why airplanes have wings is because they rely on the buoyant effect. So even though they're flying not connected to the Earth, but if they're flying and maintaining their level, they're still being pushed up. You know, that's how they're able to fly. So the air's still pushing up on the wings, keeping it steady. So in order to recreate buoyancy, you have to accelerate. So yeah, when you accelerate the airplane, it does create the pressure gradient in it. But once you're at a constant speed, then you could get up and walk around in the airplane, because the pressure gradient is not being felt anymore, because it's being overcome by the motion of the Earth, which is the push up. You know, the wings are being pushed up at the end of the day to maintain level. If you take the wings out of the airplane and you just go straight, eventually the Earth is going to come crash into it. You need the wings to maintain.
That's not where I was going with it. So, so if you're accelerating, how do you account for, I'll say it this way. So a balloon that has helium, the way that I was taught is that you have greater pressure down here. Right? And so, or you have air pressure.
Well, there's a pressure gradient on Earth.
So it's pushing, and because this is less dense, it's going to be squeezed up by the air, right? It's not.
So you think the air pressure is coming like this?
Well, it'd be coming in a chaotic gas system.
So
it'd be coming
if it was coming in from 300, then the balloon would just stay where it's at, and maybe it would just get a little smaller, or depending, right? But the thing is, it goes
No,
up.
not if there's a density gradient of air molecules.
That's the point. In order to have a density gradient, you need a container that's in motion, and that pressure from underneath creates that density gradient.
Yeah, I see what you're saying.
You can have a density gradient without a container that's in motion, basically. That's the biggest thing.
I don't have to think about what you're saying. I'm not trying to punch holes in it, which I have no problem with punching holes in things. No, I'm just, it's like a different way to think about it than I thought about it, so I have to kind of like let it compost through in my mind, you know? So but it's interesting.
No, So just before you go, one of the biggest things that globe earthers or even motionless flat earthers have to prove in order to take their claim serious about objects accelerating down is you have to recreate an experiment where you can accelerate the water bottle with the bubble without the bubble displacing. Now, could you imagine accelerating the water bottle without the bubble displacing? That doesn't exist. The bubble is always going to be displaced in the direction you accelerate the bottle. Meaning that in free fall, the bubble shows that it's not being accelerated. You know, that's why the bubble just freezes in free fall. But yeah, that's one of the, you have to come up with a force. Like people say it's electromagnetism. Flat earthers have to say that. That is electromagnetism. But again, you have to use electromagnetism to grab this bottle somehow and accelerate in one direction without any displacement. You see how the water swishes? That's displacement. You know, that's showing you that it's in motion. So you have to believe that in free fall, it's just no displacement. You know? And again, the displacement is there once it crashes into the earth or appears to crash, but it's the other way around. But that's
so you're saying that, may I touch
Yeah, definitely, yeah.
So you're saying that if it were accelerating, which is the standard model, if it were accelerating like this, the air bubble would push this way.
It would get pushed down, exactly.
But because we don't, I'm taking your word on that one, because we don't
experience that.
Yeah. Then it's not.
Then it's not, exactly.
So.
Would you like to?
No. Hold on, because I got it now. How I can say it.
Okay.
So. You would agree that air's up here because this water is denser.
Yeah.
And so if there was no gravity,
well, there was no gravity, everything would just be floating.
So, yeah. So, but if there is a pressure here, we could measure it.
We could measure it,
yes,
exactly.
And a pressure here, we can measure that,
right? Exactly, we could.
And if gravity existed, we can measure that force.
Exactly, yeah.
So, if the force of this and the force of gravity, they're going to be different.
Wait, but how can that have a force if gravity is giving it the force? Because you're saying the force of this and the force of gravity, wouldn't that be the same force? Because let me show you something now. How can we prove that this has pressure? If you were to drill a hole right here, the water will squirt out, right? Because there's pressure, right? There's weight, right? That's being registered. Let me show you this. Look what happens in free fall when you have water squirting out. This is what happens in free fall. This one's even shorter. Just real quick, okay. So this is another experiment I did again. This is buoyancy and free fall. I slow it down so you could see. So there's a bubble rising and a nut falling. But as soon as I release it, look, the bubble rising stops. And again, it's rising, 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 and then as soon as I release it, it stops moving. It's like decelerating, basically. Right? And this is what happens when I actually accelerate down. You're gonna see the bubble start to go down a bit. Watch. When I accelerate down, the bubble wants to go down. But I can't overcome the motion of the Earth. So it just comes back up again. But you could see for that second, it goes down. Look, when I accelerate down, look at that. Boom. It wants to go down, but then it comes back up.
So,
and then this is pressure. Look, pressure with water squirting out. But as soon as I release it, look what happens. There's no more pressure. Pressure vanishes, weight vanishes, everything vanishes. There's no effects of a force. All the effects of a force vanish in free fall. So the only force that we experience is up, you know, and buoyancy being that, you know. And we can recreate buoyancy again by accelerating containers in different directions, you know. Oh. But yeah, basically physics shows us that objects don't accelerate down, basically, which means a globe would be impossible, you know. Again, you have to be growing.
So there's going to be a rate of speed at which the bubble moves.
Sure.
That we could measure.
Sure.
Yeah?
I would say that rate of the bubble is a constant. You know, it doesn't accelerate, like keep accelerating. It only accelerates when it's at rest, and then it starts its motion, but then it stays at a constant rate. It just finds its equilibrium at that one, because it is again, the Earth is not accelerating, it's in a constant motion.
Well, I'll say, like, we could imagine a rocket attached to this.
Okay.
Where it goes, let's say, 10,000 miles an hour.
Okay.
Or something.
Sure.
Or if I just do this.
Yeah.
Right? Would you say that the bubble would move at the same speed in both of those?
Oh,
situations?
no. It
okay.
wouldn't.
So there's a rate at which the bubble traverses that
Sure.
space, and we could measure it if we're clever.
Sure.
And there's a rate, whatever, you know, 8 meters squared per whatever.
9.8 meters per second. That's the rate.
Yeah. Right, of the acceleration.
Yeah.
So I feel that those two would be involved in a relationship as far as that bubble moving or not, based on the speed at which the containers move. Does that make sense? I'm not saying it will at all.
No. So the speed does affect the speed of the bubble, but what also is going to affect the speed of the bubble is the substance. So if you have like a thicker substance in here, like oil, it's going to make it move slower.
Sure.
So it depends
because it's actually force.
Yeah,
it's not speed. Right?
Exactly, force. Yeah. So again, it depends on the force or the and the medium that it's surrounded by.
Sure.
So those are two variables that would depend, you know, the motion that would basically dictate the motion of the bubble. Again. Yeah. But again, you can't have motion of the bubble without any motion of the container. That's the thing. You would need a magical force like that could go through the bottle and then move the water and air without moving the bottle. That force doesn't exist. You would have to claim that water's kind of like magnetized, and there's this magnet that can move water, like, you know, it just doesn't make sense.
But the force, so you would perhaps agree that the rate of movement of the bubble, the substance in here always being the same, because I agree with you about the rate at which it moves is in proportion to the force
as well,
put upon it.
I agree.
Which was my speed with the rocket. That thing, right? So if you take the force that the Earth is pulling on it with, and the force that's being placed on it by the water, right? If one of those is larger than the other, because you see what I'm saying, you would get two different effects, whether moving and if it, let's say it was equal, it would not move. Does that make sense?
But before you get it makes sense because they cancel out. I get you. Yes. But here's the thing, you're invoking two forces now. You're invoking a force that can accelerate this down.
Yes.
And now you're invoking a force that can push the water up.
No, the force of the
you know what I'm saying? You're claiming there's a force pushing this down, but then there's also a force pushing the water up. So it's a force going in two directions at once. That doesn't make sense. Does it only be a force going down?
Well, the force pushing the water or the bubble up is not pushing the bubble up, it's pulling the water down. That's the force. So the water squeezing.
But that's the thing. If the water's being pulled down or pushed down, whatever term you want to use, then the bubble will follow that direction. You get what I'm saying? If the water's being pulled down, then the water's more dense than the air, so it should push the air down. Buoyancy goes in the direction of acceleration.
So you're saying going like this,
yes, the air bubble,
goes like that.
You go that way, the air bubble goes that way.
Which we're having gravity affect it evenly in this direction, in this on this plane, right? It's not doing this. You're not talking about.
No. Yeah.
So like this, the bubble's going to move back and forth because we have gravity being even from here to here. Well, and so canceling out, we're only dealing with the force of
left to right, and the bubble
movement.
reacts to that movement, right?
And then when we're going down, right, you have it can't go here.
But it could, though. If you manually accelerate, it does. That's my point. If you had a machine,
like this,
if you had a machine and you put it up like the height of the tree, and you actually accelerate it down, you would see the bubble go down.
Not because something's pulling that bubble down, but
it's
because the water's
pushing
going in
it
the
down.
opposite direction.
Exactly. Yes.
So now that water's pushing up with a certain force.
Well, it's not pushing up; it's the bottle pushing down on it. So it appears, the water appears. It's like when you're in a car and you accelerate, it feels like you're being pushed to the back of your seat, but you're not being pushed to the back of your seat. It's your seat being pushed against you. So that's what's happening.
Okay.
It's not the water pressing up against the bottle; it's the bottle pressing against the water.
But that force that the bottle then transfers to the water. Yes. That force, if it were equal.
Okay.
But
that's the thing, in free fall there's no upward force, is what you're saying. You're trying to say that when you accelerate this down, you actually have to contradict the upward force as well, right? That's what you're saying is canceling out. But that's the thing, when you accelerate this, when you release this in free fall, again, even Einstein acknowledged it. They even claim that gravity is not even a force anymore. It's a bending and warping of space-time. So they claim that it's not even a force. So they acknowledge that a force requires displacement. Again, the pressure transfer. They acknowledge that, so that's why they can't call gravity a force anymore. So it's just imagination. So again, what you're saying is that, there's a force pulling it down, but then there's also a force pushing it cancels out. Well, there's no force going down because even the mainstream, acknowledges that. Again, this is like the biggest.
Well, I think there is a force
going down.
In the kind of all around. Like you have the molecules, yes.
Okay.
And in a gas, they're bouncing around.
Again, I would say the air pressure we have is because Earth is being contained, not because there's a force down.
Yeah, but in here, inside the ball, let's just say this is in free fall, and you're taking a picture and you click so that we can talk about it. We take a frame.
We take a frame.
And the bubble's just right there.
Right.
Right.
Yeah, exactly.
I would say there is a force within that bubble, which is the force of the molecules bouncing around in a gas bubble.
Okay. So you would say that just by something
like if I shake up a pop and it goes.
Yeah. You increase the pressure in there. Yeah. I agree. I would say that's a little different because obviously.
But
that's a pressurized system.
It's a buoyancy. You have the interaction with the pressure of the water, the liquid, and the pressure of, in that case, air. I guess a submarine, it would be similar. And if you go down too far, it crushes the submarine. Yes.
I guess the main point I would say that even in that scenario, obviously air, when air will always get pushed up. That in my opinion shows the direction of the force of the motion.
Yeah, I follow you, and I heard that.
Yeah.
But what I'm saying is if you have this bubble in the center, it's not a zero pressure. It's not a.
So you're saying it's being accelerated without basically effects of pressure, basically, in free fall?
Well, I can kind of only think of it in the way I think of it, so that's why I'm trying to walk you through
it.
So maybe humor me.
Yeah, sure.
So if we took that snapshot and that bubble that's in the center there would have a pressure outward, right? Like if you had a vacuum and you somehow stuck the straw in there and went like this, there would be positive pressure pushing out from the air.
I get what you're trying to say, but how does that prove that?
Well, you have to take some steps with me. That's what I'm saying.
I'll accept
so,
that, sure.
Like a balloon, right? If you poke it has a greater pressure than the atmosphere.
Sure.
So if you poke a hole, the air comes out.
Sure.
Right?
Sure.
So that bubble in there isn't a void. It's not a vacuum.
No, I understand.
So you have two competing forces then when we look at that. You have the...
I would say that's surface tension.
If there's not... if they're not accelerating, but we're underneath the water.
Right, sure.
We're underneath the water,
sure.
so it's not the surface.
Sure.
So you have the pressure of the water.
Right.
Right? And you have the pressure of the gas inside the bubble.
Right.
And they meet there, right?
Sure.
So if you increase that liquid pressure, that bubble would shrink.
Yeah.
Right? And maybe disappear.
My thing is that in order to increase the liquid pressure, it needs to be in motion. That's
I know, but you're getting ahead of me. That's why I'm trying to step you through.
Okay, but you're saying that you have to imagine that there's pressure even though it's not moving. That's where I'm like, well, that doesn't happen in reality. That's my point. That, if you were to put a device that can measure the pressure inside this vessel, right? It would measure,
Well, it doesn't have to. Okay.
Let's say it was a bigger bottle, right? And we could put a measuring device inside the water to measure the pressure, right? When you release that in free fall, that pressure is gonna reach zero. When in free fall, there's no pressure. That's the point. And I get what you're saying. The bubble still stays as a bubble. Why doesn't it mix into the water, right? I don't know what you're trying to say, but. But the fact is, there's no pressure in free fall. That's what physics shows us,
So if we took a balloon that floated here, okay, because I'm trying not to transgress your view of accelerating, and you put it in a big container that we could be airtight, and we evacuated it, so it created a vacuum, right?
Okay, the
what would that balloon do?
Expand.
Yes. Yeah. So then that shows you that there is pressure inside that balloon.
What's happening there is when you remove the air, gas pressure. One of the laws of gas pressure, again, the second law of thermodynamics, is it always wants to equilibrate. Gas always equilibrates. So in order to maintain two opposing pressure systems, you need a solid barrier, right? So based on understanding that gas always equilibrates, when you create a vacuum with a balloon inside, naturally it's gonna expand because the gas wants to equilibrate.
Yeah,
it wants to
expand.
Exactly.
Yeah.
That's just the natural. That's just how gases behave.
So that bubble in there, wants to expand.
That's the thing. I don't know where you're getting that.
But you just said that it wanted to expand.
But that's in a vacuum. This is not a vacuum.
Okay.
Yeah.
So but you said gas always wants to equilibrate.
Yeah, equilibrate.
So if we had a huge column here, like we have a bubble in there, and then we have this huge column, and we put a lot more water on it, would that bubble change shape or size?
No, it would just go up. If you have a column with water and you put a bubble, it would just go up.
Poor model. So if you have, the submarine measures pressure as it goes down in depth. Yes.
Yeah,
so then, why is there greater pressure on the submarine at a lower level? Right. The submarine's full of gas.
It's actually very simple. You want to know why there's lower pressure underneath? It's the same reason why we have a higher pressure gradient on the surface of the earth than on a mountain. Is because if I was to stack bricks right here, for example, 10 bricks, and I put a scale underneath the bottom brick, and I put a scale halfway and another scale on top of the last brick, which one's going to read more pressure?
Of course, the bottom one.
Why?
Yeah.
Why?
Well,
because there's more mass
there's
above.
More mass.
Exactly.
Yes.
So that's the same principle as when it comes to the ocean and the air.
Yeah. So the water has more mass than that bubble in the center.
Yeah.
Yes?
No. Well, okay, so the reason why there's more pressure read underneath than up here is because there's more mass above.
Yeah.
So what does that have to do with the air bubble? That's what I'm trying to get. But again, in free fall, all of that becomes irrelevant. There's no pressure gradient.
I've heard you. Yeah, I heard that. So I keep talking about the bubble in the center because remember I took that frame out. So because you're claiming that bubble's not moving.
Yeah.
So then I'm like, okay, let's talk about that.
Yeah, sure.
Okay. So in that instant of time or whatever, right?
Yeah.
There is evidently an equilibrium of pressure as far as movement.
I would say that's just the vanishing of pressure. You're interpreting it as equilibrium, and and the way I see it is just there's no pressure.
But if we move it horizontal, then there's this movement of the bottom.
Right, exactly. So let me the experiment that I showed you, I moved the water bottle. When I pushed it, I literally probably didn't even go faster than 5 miles an hour.
Yeah.
And then the bubble moved.
Doesn't take much.
Quick.
Yeah.
Do you know how fast they claim this accelerates down?
Whatever.
In 2 seconds, it's 88 miles an hour. In 2 seconds. That's faster than a Tesla. That's the claim. That's 9.8 meters per second squared.
Yeah.
Meaning in 3 seconds, I'm supposed to believe that this is accelerating towards the ground by over 350 miles an hour without any displacement of the bubble. That's ridiculous. You know what I'm saying? If we drop this bottle from any height the bubble will never get pushed to the ground. And again, it's because people will say, oh, but if I release this here, it's a small impact. And the higher I release it, there's a bigger impact. So it's an acceleration, right? The fact is, it's a deceleration that's happening. So again, if this is going 1,000 miles an hour with the Earth, hypothetically, as soon as I release it, there's a deceleration that happens. So the more time it has to decelerate, the bigger the impact is going to be.
So you could do it. Is the bubble staying, not moving, invariant to how far the free fall is? Do you understand what I'm asking?
Yeah, I get what you're saying. So yeah, it would just stay still.
No matter if it drops for a mile.
Some people claim that after 5 seconds the bubble.
Well, I don't know. Yeah.
No. Some people claim that, but I just think that's funny. But some people do claim, oh, you have to drop it from 5 seconds, you know, and then the bubble's gonna start moving, you know. And it's like, I think at 5 seconds you will have to drop it from like a really tall building, like a
sure. But it hasn't been. I mean,
that test happens.
You can drop it from a balloon with a camera attached to it. You can see, but science has not done this.
No, and they actually recreated their whole. That's the whole reason why Einstein had to come up with his theory, to acknowledge the fact that doesn't happen. That's why Einstein came. And I don't know if you knew, but the mass attracting mass theory of Newton's theory, they don't even use that anymore. Basically, it's just. It's again, that's why they use the modern theory of relativity now, because they acknowledge that fact, you know. Yeah.
I just wanted to see what you were all about.
No, yeah. So here, I could give you the flyer.
Sure.
Yeah.
Well, it's been interesting talking to you, and I appreciate it.
Yeah, you take care.
Well, I'll think about what you had to say.
Yeah, definitely, man. I appreciate the talk, man. Yeah.